Okay, so I'm going to start here. I'll start now. It's joint with Atticus Stonestrom, who is a student. In fact, he did a lot of the, well, never mind, he did a lot of technical work in the paper. And there's no pre-archive thing, but there's something in preparation, hopefully sometime soon. Thanks to best wishes to Frank for his birthday, and maybe tonight in the banquet there's time to say a few things. I hope, yes, so I'm not going to say too much now. Other than that, I met Frank first in '87 in this Trento conference. Maybe it was the first one. There was a very nice Trento meetings, maybe 2 or 3 meetings. I forget how many there were, 2. Annalisa Marcia used to organize them. Anyway, so I first met Frank there, and we've been close mathematically and personally since then. So I'll say a bit more tonight, okay? Hopefully. So it's nice to talk about this material in this particular conference, as it involves all the words in the conference title, right? What's it? Model theory, groups, combinatorics. The title of my talk that I gave here is Quasirandomness, was it? What was it? Quasirandomness is something. And I think in the title I put on the schedule was arithmetic regularity, but it's the same content, right? It's just another word for the same thing. The general idea, which has been around for some time, is to adapt Tau's so-called algebraic regularity lemma for graphs definable in finite fields uniformly, to pairs to this arithmetic environment of pairs GD, G a group, D a subset of G, defined uniformly in finite fields, right? So, and by the way, the Tau algebraic regularity lemma, you know, the kind of input of model theory to this general area, I think there's 2 things started it. I mean, I think one is Maliar-Echelar, and the other is this, I don't want to say I started it, but with Starchenko, we kind of gave a model theory proof of Tau regularity lemma, and using simplicity, simple theories, and then I think Udi the same. In fact, before I left Leeds, I told, in a seminar about this in Leeds, and I told Dougal, I said, we can do this, baby. And he said, who are you calling baby? Then he said, I said, sorry, Dougal, we can do it, Dougal, and he didn't believe me. Dougal didn't believe me. And so then I said, well, no, we can do this. We can do the general all characteristics. And is Dougal here? You didn't believe me, did you? No. But whenever I told Dougal something about model theory, he said, no. He believed nothing I said. And then we came to Notre Dame, and then I sort of talked to Sergei and had a seminar also about it, and we saw what to do. Anyway, this is about the arithmetic version. And it's been around for some time, and then we decided to try and do it with Atticus. And so Tau's improvement on the conclusion of Semeredi regularity, graph regularity, was 2 things. So he was talking about graphs defined uniformly in finite fields, okay? And there were 2 improvements. Of course, this is not all finite graphs, it's special things, and the improvements were so-called power saving, which I'll talk about, number 1, and also no exceptional pairs. No exceptional pairs, which is what Julie was talking about this exactly, you know, when you can, you know. Good. Now, the so-called regime, I don't know why the word regime is used a lot, but I use it too sometimes. Of looking at pairs GD is often called the arithmetic regularity regime. Started by Green in 2005, which Julia referred to, talked about his paper, and continued by Caroline, Terry, and Julia Wolf in the stable finite field model environment, then by Gabe, Caroline, and me, stable NIP, and then much more has gone on, including a recent functional stable version with Gabe, which I think I'm not going to talk about here, but Amador may touch on this. I don't know, you told me. You may mention it in your, an analytic functional version, in place of a group, finite group and a subset, it's a finite group and a function to the reals. The function replaces the subset. Anyway, to a pair GD, just a group and a subset, you can associate a bipartite graph, G. So we're looking at finite fields in the ring language, and we're looking at pairs GD, G a definable group, uniformly definable group, D uniformly definable subset, okay? And to this data, you can associate a certain bipartite graph, GGE, where E, the edge relation just says xy to the minus 1 is in D. So there's a bipartite graph you can attach to a, and you can apply, so this is a bipartite graph, uniformly definable in finite fields, you can apply tau, the tau algebraic regularity lemma, which gives this nice decomposition. Okay, but what's the improvement here? So the main point is that when we do this tau algebraic regularity lemma applied to this bipartite graph, usually regularity lemma, what's it do? You have a V and you have a W, and you want to decompose V and W into certain, partition them, and you get a bunch of induced subgraphs, VI cross WJ, and the statement is about that these are regular, essentially, and no exceptional pairs, a few other things. And the main point is you can decompose, in this context, you can decompose to be compatible with a group structure. That both the decomposition of V and of G and G, both two sides, is with respect to the same, to cosets of a given normal subgroup. Okay? This is the idea you can get. So it's the optimal, you get an optimal compatibility of the decomposition of the associated bipartite graph with a group structure. Okay, this is the. Any questions? I'll give some more. Now, I didn't give all the background, but I will now state results in a rather clear, hopefully a clear form. I'm sorry that I wrote this yesterday. That there's too many definitions in what I've written. It's overladen with definitions, and I apologise because it's things definitions that I don't even understand myself. The definitions, actually. So, okay. Anyway, I'll now try, and what I'll do is I'll try and state the theorems, and then explain what the words mean, and then talk about some connections with other things, then talk about methods. Right. So, we have these expressions, epsilon quasi-random, epsilon regular, epsilon uniform. These expressions will be applied to two kinds of things, finite bipartite graphs and subsets of finite groups, okay? And we'll see the compatibility, how it works out. And these expressions are somehow essentially synonymous. And I don't know, I mean, Julia uses uniform a lot, Green uses regularity a lot, regularity, Gowers uses quasi-random. So as far as I understand, the notion quasi-random is a notion is meant to describe objects which are not random, but satisfy properties of random objects. This is more or less right, that's the idea. Right, so here's the statement now. Theorem 1. Given M, there is a C such that for any finite field F and D subset of G, definable of complexity at most M. Complexity, I'll say in a minute, this is the complexity language of what tau uses. It just means the number of symbols in the formula defining D and G, right? In the language of rings. Given D and G, both definable of complexity at most M in F, there's a normal subgroup H of G, definable in F, with complexity at most C, and index at most C, such that for any two cosets VW of H and G, you restrict the corresponding bipartite graph to V and W, and you get something which is C size of F to the minus a half, quasi-random. I've got to define what quasi-random is. Okay? That is the statement. That's the statement. And there's no epsilon here. The point is there's no epsilon. I mean, the thing is, as the field gets bigger, you get a better degree of quasi-randomness. Okay? Question? Professor Ben Jacob, you're looking like something like you're looking a little bit spaced out, as they say. But you always look spaced out, but more than usual. So what? Oh, okay. Okay, sorry.
So is this the regularity theorem, or this is like a part of it?
No, that's it. That's the one. That's it.
How do you get the partition? You're supposed to get the partition of the graph and so on.
That's it. That's the partition. That's the partition, right? So you've got. This is it. This is it. You've got G. Can I write? Should I write with the board something? What should I do? What should I write with the board? What should I say? I don't know. I mean, I don't know. I don't get it. I mean, look. You've got G. You've got G, G, E. Right? Can G, G, E. G, G, E. That's my, right? And E comes from x, y to the minus 1 is in D. And the decomposition usually is you get, with G is say V1, Vn. The first G, the second G is W1, Wn, or M or something. And the subgraphs are VI cross a VI Wj with the E restricted to that, right? But here, all of these people are simply the cosets of a given subgroup. So the VI, Wj are cosets. And that's what I mean by having the optimal result in terms of compatibility with the group structure, okay? Yeah? Yeah. You can ask the question, but I don't know. I didn't think about it. It's a very good, very nice question. Thank you, Amadou. But I didn't think about it, okay? So complexity, I'm saying here, can be read as number of symbols in the language used of unitary rings defined used in the formulas defining the data. That's complexity. So if you if you think there's only finitely many formulas, symbols in the language, what it says, it's a uniformity statement about uniform definability. You're given, say, a formula phi xy or a delta, a finite collection of formulas, phi1, right? And then there's a psi, such that for any pair GD defined using the first set of formulas, right? There's an H using the second formula. So you can restate in language of uniform definability, which is a natural moral theoretic context. Here's a Fourier analytic restatement. So it's very nice that Julia talked about Fourier analysis, and so I'll state a Fourier analytic restatement, and I'll define these things a bit later. Okay? I mean later. I mean today in the lecture. I don't mean like tomorrow or something. Okay? So, given M, same thing. There is a C such that for any finite field F and group G definable in F and definable subset D of G, I should have said, of complexity, I should have said there, G and D definable with complexity at most M. I forgot to say it, right? So D, same constraint on D and G. There's a definable normal subgroup, H of G, of complexity at most C, such that you take any right translate of D, intersected with H, then all the Fourier, it's a C size of F to the minus an eighth quasi-random subset of H in the Fourier analytic sense that Julia talked about. The trouble is this is not abelian groups. So the Fourier analysis is a kind of non-commutative Fourier analysis. It says that the Fourier coefficients of the indicator, so for each right translate of D intersected with H, the Fourier coefficients of the indicator function, right, one indicator function, are bounded by a certain number. So it's exactly what Julia was saying about the Fourier coefficients in the case of f2 to the n bounded by epsilon. But here, there's no epsilon. Just the epsilon gets smaller as you, yeah?
Yeah, well, I guess you're thinking of the size of your field is going to...
Yes, as the field, so the point is, the epsilon business is not, there's no epsilon, but the point is that the data is about the size of the field. The bigger the field, the better you get, okay? So I'll try and state what these things are and the relationships. We'll give some definitions of relationships taken partly from Gower's quasi-random groups, which is a paper, I don't know, middle 2000s. It's funny that Atticus knew this stuff because I think you were in Oxford. You were doing a project on product-free sets, and so he knew the paper. And anyway, so right. Let's define quasi-randomness of an arbitrary finite bipartite graph. So VWE, finite bipartite graph, let D be the density of the graph, the number of edges defined by the number of possible edges. And we call the graph epsilon quasi-random if that, what's there, right? You add, for all pairs V prime, on the V side, you look at the cardinality of the intersection of the neighbors of V in W with neighbors of V prime in W, square it, it's less than or equal to this D plus epsilon size of V squared, size W squared, right? It's a bit of a thing to see, but sorry, that's one of the definitions, but I'll try and explain a little bit. This is a definition of, whose definition is it? I don't know. I think it's a quasi, I think it's a, let's see. Yes, this notion has origin comes from Chung, Gray, and Wilson for unipartite graphs. So the quasi-randomness was defined for unipartite graphs. They have a paper about quasi-random groups, I think, or something. Chung, quite a long time ago. That's it, but I'll try to explain a bit better, so it's hard to maybe parse this exactly. But I mean, conceptually, it tells you something about the size of intersection of neighbors of V and neighbors of V prime. And actually, now you can do the same thing, but reversing the roles of V and W, and it's turns out to be equivalent. Okay, you do the same thing, but now W prime. Okay. The main fact, one fact, which is not hard, is that first thing, quasi-randomness, epsilon quasi-randomness of VWE implies epsilon to the quarter regularity of VWE. So now we get this regularity. What's regularity? Regularity, epsilon to the quarter regularity says that, what I said, for any subsets A of V and B of W, look at the size of look at the edges between A and B divided by size of A times size of B. So this is in some sense this is the density. Yeah, this is the density. So you have A and B inside V and W. You get an induced subgraph, A, B, E, restricted to A, B. It says the density of that graph is close to the density of the full graph, which is D, in the sense of less than or equal to epsilon to the quarter, V times W, size over size of A times size of B. So the point is that, yeah, that's the statement. Okay? Now, what is this? What's the last thing really mean? This last, God, I don't know, where's this pointer? I mean, where, that's it?
I wouldn't,
You don't like it.
Pardon?
I don't think you want to use it.
Why?
Because you didn't want other people use it.
Yeah, okay. I mean, I was going to point at my thing here. So, yeah, that's it. It's the difference between, the left-hand side is the difference between the total density of the graph and the density of the induced graph, and it gives some bound of that. Let's restate a little bit in a nicer way. So what this last thing says is that if you take A and B subsets of V and W, not too small, size being greater or equal to epsilon to the half of v, epsilon to the half of w, then the difference between the density of the induced graph on vertex sets A and B and the full density is at most epsilon to a half. So this is the usual comprehensible meaning of regularity. That a graph is regular if you take sufficiently large, if you take reasonably large subsets, then the induced graph has roughly the same density as the full graph. Okay, this is the quite clear meaning of regularity. Okay, so I've got that epsilon quasi-randomness implies epsilon to the half, epsilon to the quarter regularity, and also on the other hand, epsilon regularity implies 12 epsilon quasi-randomness. So these are what they call like polynomially equivalent. These notions are polynomially equivalent in a very strong sense. Now, quasi-randomness of finite subsets of finite groups is widely used in additive combinatorics on abelian groups. Okay. I'm discussing a version for possibly non-abelian groups. Now, some of these equivalencies I'm going to state are implicit in this paper of Gower's, but not explicit. So we kind of, Atticus had to check a few things. Any questions, by the way, so far? I'm not sure if I'm going too fast or too slowly. How long do I have, by the way? 10 to 11, so half an hour more. Am I going too fast? I don't know. I don't know. I feel okay. What? I don't know. I'm not. 1, 2, 3, 4, 5. 1, 2. I'm trying to compute. 1, 2.
If you finish before time, nobody's going to be in.
2, 3, 4, 5. No? Okay. Okay, so let's discuss this quasi-randomness subsets for non-abelian groups. So given a finite group, H, let H hat be the set of irreducible, complex, unitary representations of H. Okay, so homomorphisms to some unitary group over a five-dimensional vector space. Then for a complex valued function on H, the Fourier transform in this context hat f of f is a map on the irreducible representations. It takes any pi to 1 over the size of H, sum H in H, f of H, pi, H to the minus 1. This is the definition of the Fourier transform of this f. So this is an endomorphism of V sub pi, and V sub pi is just the underlying vector, the underlying vector space of the representation. Okay. Good. Now the Fourier coefficient of f at pi is this f is the norm of f hat of pi, operator norm, which is the max of the, so T operator is the max of the norms of T a vector, T a unit vector, if I'm not mistaken. And we're going to call the subset of the group H epsilon quasi-random, so this is a notion now for a subset of a group, epsilon quasi-random, if for all non-trivial pi, irreducible representations, the Fourier transform of the indicator function of d to the minus 1 of pi is at most epsilon. You rewrite this as the sum, you can rewrite this as, look at this, if you think of what it means, so by indicator function I mean the function which is 1 on the set it concerned and 0 otherwise, right? So if you look at what it means, it just says that the sum, the norm of the sum as h goes over d of pi of d, where h and d in the set concerned is at most epsilon times the size of h. Okay, so that's an explicit definition of being epsilon quasi-random. For each pi, for all, sorry? So it's like what Julie was saying, but this is non-commutative version. Is that okay? Yep. So it's the non-commutative version, just using, right? So in the commutative version, you're just using characters to S1, right? But but maybe there's nothing to S1, so you look at these other representations. Good. Then the relevant facts are that if D, what's the relationship between quasi-randomness of D in this Fourier analytic sense and quasi-randomness of the associated bipartite graph, which we talked about before? Okay? So the statement is that if D is a subset of a group, this finite group is epsilon quasi-random in this sense, then the graph, the associated bipartite graph, is epsilon squared quasi-random as defined previously. One fact. This is done explicitly in the paper that we're writing. And on the other hand, if the associated bipartite graph is epsilon quasi-random in the previous sense of graph quasi-randomness, then the subset D of H is epsilon to a quarter quasi-random. So that's the relationship between quasi-randomness of subsets of groups and of the associated bipartite graph. So the conclusion of corollary 0.2 is that you have this, so again you have given M, there's a C, the data, for any data is a pair DG, definable in a finite field with complexity M. And the statement is there's a definable normal subgroup H of G of complexity index at most C, such that for every G in G, a non-trivial irreducible representation, the norm, you look at some H, you translate D into H. It's like, doing this is like looking actually, so what I'm doing to translate D into H, it's like looking at the intersection of D with different cosets of H. I'm just moving everything into H because now you're a subset of a group and you could talk about this. Otherwise, you want to talk about quasi-randomness of subsets of cosets, which you can do, but I'm just doing it in the... So it says that for every translate of D, translate, intersection H, you get the sum of little h in that H intersection of translate of pi of H is bounded by C size of F to the power minus 1 over 8. And again, you get better things that as F goes to infinity, size of F goes to infinity. Okay? A few comments. In the usual Semeredi graph regularity, so I'm just saying, I'm kind of making explicit some things I was saying informally. In usual Semeredi graph regularity statement and the tame variance, by the tame variance I mean the stable variance, the NIP variance. Right, so Semeredi graph regularity is about all finite graphs. Okay, everything. Then you can insist, then you can say, okay, I look only at finite graphs where the edge relation is k-stable. Okay, or you look at all finite graphs where the edge relation is k-nip. Those are the tame variants, and you get improvements. This is the theme that Julie was talking about. So in the usual Semeredi graph regularity, you give an epsilon in advance, then you find an n, depending on epsilon, such that for any finite bipartite graph, you can partition it in the way I described, V1 to Vn, W into at most n, each vertex set's decomposed into at most n things, so you get n squared subgraphs outside some exceptions, the exceptional set, or these subgraphs are epsilon regular, or even better in the tame case, epsilon homogeneous. Okay? This is the epsilon. Now here there's no epsilon at all. So the epsilon works for all the finite graphs you're concerned with. Here we're looking at the graphs defined uniformly in finite fields. As the field gets bigger, we get better regularity. That's it, right? And this is I think it's what they call power saving. Am I right? Pardon? What's it called? Say it again. Square recancellation. Okay. But I heard the expression power saving, which I didn't. That's also good. Yeah, I did. But that's what they call power. So it's a fundamental improvement over the right. So as the field gets bigger, you get better regularity. Okay, that's one thing. And in both Tau's algebra regularity lemma and our theorem 1.0, it should be 0.1. There's no epsilon in advance, and the degree of regularity gets bigger as the finite field gets bigger. But of course, we're staying with the same formula defining the data. Yeah? Moreover, there are no exceptional pairs. Right? We get regularity of all the pairs. And as mentioned in the arithmetic case, the decomposition, so in our context, the decomposition of the associated bipartite graph is compatible in the best possible sense with the group structure. That's what I gave over here, that your V1 to Vn, W1 to Wn, or GG of GG, and its decomposition is on both sides of the bipartite graph, G and G. The decomposition is with respect to a bounded index normal subgroup, definable uniformly. Okay, comment? Now, one may have expected, Bohr neighborhoods to crop up, as they do in Green's. So Green has this general, I'll talk about his general paper, which is general theorem for arbitrary abelian groups, which Julia referred to. And to be, the general theorem, as I still don't understand. I mean, does anybody understand that statement? Who? You? Yes. Can we talk a bit later? Maybe a lunch or something, yeah, a little conversation about that. No, because we tried to make sense of it. There's a special case of the finite field model. Anyway, in general, you will get these kind of Bohr neighborhoods. A Bohr neighborhood is you've got a group, finite group, and you get a map into S1 homomorphism, and you look at the pre-image of a little ball. And it's called a Bohr neighborhood. And you have to deal with these things in general. And we deal with this stuff in general in the NIP context of tame arithmetic regularity, but not in the stable context. We can stay with just subgroups. So the reason is that we don't have we do not. So as expected in all this stuff, the proof is a non-standard proof. It means going to a pseudo-finite field. And you're in this nice environment, super simple environment, and if you have a definable group in a super simple theory, the G00 is the G0. So the Bohr neighborhoods model theoretically come from the compact group G mod G00. That's where the Bohr neighborhoods come. It's like an approximate subgroups, the so-called Lie model. Where it comes from G mod G00. And it's a compact group, not necessarily finite, not necessarily pro-finite. But in the super simple context, the 0 equals the 0. The smallest over some parameters type definable subgroup of bounded index of a definable group is actually intersection of definable subgroups of finite index. So this is why it's amazing, this is why you are able to get this. So it's really nice. I mean, you've got this connection, you've got this quality randomness of subsets. It connects with the quality bipartite graph, and everything is about the graph in terms of the coefficients of a subgroup, right? It's just fits together very nicely in this context, but it doesn't fit. This kind of thing will not happen in general, even for abelian groups, in the general arithmetic regularity. Okay, this is why connections. Let's make a few connections. So theorem 0.1, the main theorem, appears to be a powerful statement, right? The main theorem appears to, I don't know, and should have some consequences that we have not explored. I don't know. Maybe we can talk. What? What's funny? Oh yes, I'm sorry about this. I'm sorry, Daniel. So I put apologies to Daniel, but I'm just saying that that an example is the result at the end of Daniel's talk about having many elements beginning three arithmetic progressions, or progressions, is it can follow. We talked about this with Atticus, and it follows. Pardon? The corollary, right? The corollary, whatever it, yeah. We talked about it. So for example, you can get these just from this regularity statement. Let's first note that you look at definable groups in finite fields defined uniformly. They're essentially algebraic groups by something that I did with Udi a long time ago, a paper called Definable Subgroups of Algebraic Groups over Finite Fields. Right, so it means that a group definable in a pseudo-finite field is virtually isogenous definably with the points, the k points, f points of an algebraic group. So essentially, the groups we're dealing with are algebraic groups. Okay, so it's definable subsets of algebraic groups of the finite field points of algebraic groups. And there are two extreme cases. One is semi-simple, and the other is commutative. There are two extreme cases of algebraic groups. So here we're thinking about an algebraic group defined by a formula, maybe over Z, and then we look at the points of that in a given field. So let's just say what is going on. Let's consider the first case. Take G to be a simply connected, semi-simple algebraic group defined over Z. So defined over Z, I can, for any finite field, I can kind of, look at the points of that, even in the finite field, which means you reduce, right? You do a reduction to characteristic P, and then you look at the points of the finite field, right? So that's a typical. So G, the collection of GF, So you fix such a G, the set of GF, F a finite field, is an example of a uniformly definable family of groups in finite fields, right? In a trivial way. There's not even any parameters we have to deal with. It's just the same formula. And so the point is that, assuming some good reduction of some kind, GF, as F varies, there are no uniformly definable finite index subgroups of GF, which means of a given index, we have to be given index, right? So that means that in a pseudo-finite field, there's F points of G has no definable subgroups of finite index. It's by simply connectedness and, okay. Again, coming out of the paper with Udi. So it follows that by theorem 0.1, if you apply theorem 0.1 to this G into some subsets, you cannot pass to an H other than G itself, right? There's no H. There's an H, but H is G, right? There's no finite index definable subgroups. So it means that already, you look at your subset D, definable subset of complexity of most M, it's already C F to 1/8 quasi-random inside G. So it says that every uniformly definable subset of GF is quasi-random, getting better as you get a bigger finite field, right? Looks like a strong statement. On the other hand, in the Gowers paper that I talked about, there's a notion of quasi-randomness for finite groups. So I've talked about quasi-randomness for subsets of a finite group. There's a related notion, quasi-randomness of the finite group itself, which is not the same. It doesn't mean that the group itself is quasi-random in the earlier sense. It means something else. There's a notion of quasi-randomness which says that G is D. Daniel talked about this in one of your papers, yeah, about this. That we call G, D is a number. We call G D quasi-random Well, there's different characterizations or different equivalent notions of equivalent characterizations, and one of them is G is D quasi-random if it has no irreducible unitary non-trivial representation of dimension less than D. Yeah? So no abelian group is D quasi-random in this sense. And a couple of things are proved and observed. If D is the minimal dimension, so here, yeah, if D is the minimal dimension, or minimal dimension, I mean minimal, not minimal, dimension of a non-trivial irreducible representation of G, then every subset of G in the previous sense is D to the minus a half quasi-random. All right, as defined earlier. In the special case of SL2, which Gowers talks about, for every finite field, SL2 of F, finite field FQ, SL2 of FQ points is Q minus 1 over 2 quasi-random. So every subset of it is 2Q to the minus a half quasi-random. Okay, so Gowers has there are better results, right? So at least in the case of SL2. So there should be related computations of the degree of quasi-randomness of arbitrary semi-simple algebraic groups. I don't know if this is, in which case this theorem 0.1 may not say too much new. Okay, so again, you conclude from theorem 0.1 if you take every definable uniformly subset of GF, F of finite field, defined uniformly, is quasi-random. And if you have control over representations of the Q points, of the F Q points of any semi-simple algebraic group, then using this previous thing about in terms of its, then anyway you can get. So you need semi-simple. So I'm not sure. We're not sure in the case of semi-simple groups that we say anything new. I don't know, but at least we say something. But maybe it's okay. That's one issue. Now the abelian case, and this connects very much with what Julia was saying. So Green's. Let's state Green's. So in the Green's paper, Semeredi type regularity lemma in abelian groups, he has a general lemma which involves sort of broad neighborhoods and through analysis, but there is a special case which is the finite field model. He states the case of where you limit your finite abelian groups to vector spaces over F2 of higher and higher dimension. It's the finite field model over F2. So I say that the actual result in the general case, abelian case, is about all pairs GA, G a finite abelian group. That's the main theorem. But in the special case, when G varies over among finite dimensional vector spaces over FP, I'll say FP, he does F2, Semeredi regularity for G, X minus Y and A, does apply in the optimal manner. So this is general, right? Apply in the optimal manner in the sense of the decomposition. You get compatible with group structure in terms of a subspace, is what Julia was exactly, very nice Julia explained all these things. So fix P and I'll do it for P and E. Fix P and epsilon. Here's a statement for arbitrary P. There is a C such that for any N, if G is Fp to the N and D is an arbitrary subset of G, there's a subspace, or a subgroup subspace of H of G. R, I should have said of error, typing error, a subspace of index at most C. So H has index at most C. So outside a small exceptional set, for each of these cosets, VW of H and G, the corresponding bipartite graph, VW, X minus Y and D, is epsilon regular. This is Green's statement, okay? So it's P is fixed, N moves. We're looking at we're talking the same time about every possible subset of Fp to the N as N moves. Right, what can we say about that? Well, notice that the groups Fp to the N as P varies are precisely the additive groups of the finite fields Fq. Precisely. All right? Is that right? So we're looking just at one group, the additive group, as the field varies. So we can apply theorem 0.1. To get that for any m, there's a C such that for any finite field f and definable subset D of complexity of most m of f of the additive group, definable subset of the additive, let's call it f there, there's a subspace H of index at most C such that all cosets, for all cosets, no exceptional sets, VW of H in F plus in the group, additive group, you get C f to the minus 8th regularity. Okay, so right. So this is like, this complements in some sense green. Okay, but so what is the difference? The disadvantage is we're only talking about uniformly definable subsets. Disadvantage. The C depends on M, on the complexity of the formally defining D. Okay.
But it does not depend on the characteristic.
No, so I'm going to say this now. The advantage is you get uniformity in P, which is not in green. There's uniformity in P statement. So the disadvantage, you're talking about definable subsets uniformly. The advantage is you get uniformity in P. Right, you see what I mean? And you get power boundedness, or power saving rather, with no exceptional pairs. So there's a disadvantage and an advantage, right? So it's complementary to green, but the advantage is you get uniformity over P. You get a statement for all Fp to the n, all P, right? Because it's the same group, additive group. Yeah.
Like you can adapt Green's proof
Yeah.
to give a statement for all P.
Yeah.
The index will depend on P, but also here your regularity will depend on P.
Pardon?
Because you have the size of the additive group F here,
Yes.
and that depends on P. So if I fix that
No, but
epsilon, then I will get a dependence on P in the
no, but the index. I'm talking about the index of the index is independent.
Right, but if I turn this into a statement in the spirit of green,
Yeah.
where I replace your regularity conclusion by an epsilon,
Yes.
then that turns the bound on the index into a function of P.
It's right. Okay. Okay.
So
I think it's nevertheless a very nice statement.
Yeah.
What about this right about uniformity? What do you do not assume uniform definability in this?
Pardon?
Sorry, I'm asking because you said about this disadvantage about
Yes, we're not talking about arbitrary subsets of Fp to the n. We're talking about uniformly definable subsets of Fq as Q varies, and the same formula is defining the D.
So I have a question.
Yeah.
Your theorem is only for groups with subsets of the field, not subsets of F to the n.
What?
Why did you have to go to FQ here? Couldn't you do it for FP to the n?
No, because Fp to the n. We want an algebraic group, right? And uniformly, an algebraic group is this Fp to the n. Is a Fp to the n is not uniformly definable explicitly. Fp is vector space over Fp. As n varies, it's not uniformly definable, right? It's different. It's got different dimensions. Okay, but the additive group is, yeah.
Another question: your H, was it not definable in your CO1?
Yes.
It's not.
Pardon?
In F, you cannot define a sub. I don't understand. H is not definable in the field F.
H is defined.
Yes. I didn't say that. Okay, look. Can I say some? I'm on time. I'm on time. I want to say something about methods. So methods. Some key points. Key points. As usual, we prove a theorem in pseudo-finite fields, and use the pseudo-finite yoga. By the way, there is what I call this. Going back. By the way, one ideological point I want to make. Maybe I can take another couple of minutes. Sorry. No, I'll stop whenever you want me to stop. I'll just stop. When you say stop, I'll stop. Put up the sign, I'll stop, okay? But one ideological point about all this regularity stuff that I made, I wrote something called Domination Regularity, a survey paper, which is some point a few years ago, it's an ideological point that this is not about the key issue with all this tame regularity. It's not about applications of model theory. These are restatements of structure results in model theory, right? So it's not application of, it's simply a restatement of structure results. For example, the stable graph regularity, if not the way that Mallias and Shellard did it by playing with this 2-rank in a finite context, but in the pseudo-finite point of view, is that the content is just that in a stable theory, a Kiesler measure is a weighted sum of Dirac's. That's it. This is the content of stable regularity then. So likewise for the arithmetic versions. It's restatements of structural results. Modulo is playing around with pseudo-finite and back and forth. So that's one ideological thing. Anyway, yeah, that's right. So F is a saturated, we work pseudo-finite field, G group definable, D defined over M subset. We may also use G to denote the points to the bigger saturated model, and we have a non-standard counting measure. Generic means maximal dimension in the sense of the geometric structure pseudo-finite field. It's super simple of SU rank 1. Dimension independence agrees with forking independence, non-forking independence. In fact, in the paper, we're making it a bit explicit because I couldn't always find a great reference for this, although anyway, it's something well known. And what Daniel called the PQR theorem, in the form he stated it, is due to Amador and me. I'd forgotten. There was a paper of Tom and Frank. So this is the connection with Frank. With Frank is this paper about super simple fields. In fact, there's still open questions about super simple fields. Very nice open questions for a long time about being PAC. There's really beautiful questions which we didn't hardly touch. Anyway, PQR theorem is, and then it's about the generic types inside G00 or inside G0 in simple theories. And we did and then with Amador's thesis, we did a version of that about, which Daniel talked about outside G00. Right, that's it. I don't know. That's the statement. There you are, right? So good. Second point is that if BC realize generic types over M and are independent over M, so this is the context. The group, the definable subset, okay? Okay, all right, so. If these are generic types over M are independent in the non-forking sense or whatever, then the measure of the intersection of the translates BD and CD depends only on the cosets of BC modulo G0M. This is stability of a certain formula. Okay, so that stability plays a role. Okay, anyway, I say a little bit more, and so I'll stop here. Okay, thank you.